In this outcome, we look at how atoms join together and why the type of bond they form decides what a material is actually like. Get the bonding right, and the properties, melting points, conductivity, hardness all start to make sense. So why do atoms bond at all? The simple answer is stability. Atoms bond to reach a lower energy, more stable arrangement, usually a full outer shell of electrons, like the nearest noble gas. Only the outer or valence electrons are involved. There are three main types of bonding to keep in mind: ionic, covalent, and metallic. And crucially, it's the type of bonding that controls the properties of the material. Let's define the three bond types up front. An ionic bond is the electrostatic attraction between oppositely charged ions. A covalent bond is a shared pair of electrons between two atoms. A metallic bond is the attraction between positive ions and a sea of delocalized electrons. And the valence electrons, the ones doing all the work, are simply the outer shell electrons. Dot and cross diagrams are a neat way to keep track of where the bonding electrons have come from. We draw electrons from one atom as dots and those from the other as crosses, showing only the outer shell. Of course, electrons are all identical. The labels don't mean they're really different. They just let us follow how each atom's outer shell gets filled during bonding. In ionic bonding, electrons are transferred outright. A metal loses electrons and a non-metal gains them, forming positive cations and negative anions. Sodium, for example, loses one electron. Sodium goes to a sodium ion plus an electron. Chlorine gains one. Chlorine plus an electron goes to a chloride ion. Those oppositely charged ions then attract each other strongly in all directions, and that attraction is the ionic bond. Let's build sodium chloride with a dot and cross diagram. Sodium's configuration ends 3s1, so it has just one outer electron, which we'll show as a dot. Chlorine ends 3s2, 3p5, so it has 7 outer electrons, drawn as crosses. Sodium hands its single outer electron over to chlorine. That leaves a sodium ion with an empty outer shell, written as sodium in brackets with a plus, and a chloride ion whose outer shell now holds 8, its own 7 crosses plus the one transferred dot. So we end up with a sodium plus and a chloride ion side by side. Now magnesium oxide, where 2 electrons move. Magnesium ends 3s2, so it has 2 outer electrons, while oxygen is 1s2, 2s2, 2p4, and needs 2 more to fill its shell. So magnesium goes to a magnesium 2 plus ion plus 2 electrons, and oxygen plus those 2 electrons goes to an oxide ion, O2 minus. Both electrons pass from magnesium to oxygen. Because the 2 plus and 2 minus charges balance exactly, the formula is simply magnesium oxide, and the oxide ion shows 6 crosses plus 2 transferred dots, 8 in all. Covalent bonding is different. Here electrons are shared rather than transferred. 2 non-metal atoms share a pair of electrons that is attracted to both nuclei at once. A single bond is one shared pair, as in hydrogen, H to H. A double bond is 2 shared pairs, as in oxygen, O double bond O. And a triple bond is 3 shared pairs, as in nitrogen. The more pairs shared, the stronger and shorter the bond. Let's apply that to hydrogen, oxygen, and nitrogen. Hydrogen has 1 outer electron, so 2 hydrogen atoms share a single pair to give H to H. Oxygen has 6 outer electrons and needs 2 more, so 2 oxygen atoms share 2 pairs, making the double bond in oxygen. Nitrogen has 5 outer electrons and needs 3 more, so 2 nitrogen atoms share 3 pairs, giving the triple bond in nitrogen. In every case, each atom ends up with 8 electrons in its outer shell. So hydrogen has 1 shared pair, oxygen 2, and nitrogen 3. There's a special case called dative covalent bonding, where both of the shared electrons come from the same atom. One atom donates a lone pair into another atom's empty orbital, and we show it with an arrow pointing from donor to acceptor. A classic example is ammonia reacting with a hydrogen ion to form the ammonium ion, using nitrogen's lone pair. Once it's formed, though, a dative bond is completely identical to any ordinary covalent bond. Let's see how the ammonium ion forms. In ammonia, nitrogen has 3 nitrogen-hydrogen bonds and one lone pair left over. A hydrogen ion, meanwhile, is just a bare proton with no electrons and an empty orbital. Nitrogen donates its lone pair into that empty orbital, creating a 4th nitrogen-hydrogen bond, a dative one. The overall plus charge is spread across the whole ion, and importantly, all 4 nitrogen-hydrogen bonds end up identical in length and strength. In a metal, the atoms release their outer electrons, leaving behind a regular lattice of positive metal ions. Those freed electrons become delocalized, free to move throughout the structure, forming a kind of sea of electrons around the positive ions. The attraction between the ions and this electron sea is the metallic bond. Picture rows of positive ions with mobile electrons drifting between them. Let's name the 4 main structures. A giant ionic lattice is a repeating 3-dimensional array of alternating cations and anions. A simple molecular structure is small molecules held together by weak intermolecular forces. A macromolecular, or giant covalent, structure is a huge network of atoms all joined by covalent bonds. And a delocalized electron, again, is one free to move through a metal lattice. Let's compare those 4 side by side. Ionic solids, like sodium chloride, are giant lattices of ions held by strong electrostatic attraction. And metallic structures are positive ions in a sea of delocalized electrons, both with very high melting points. Simple molecular substances, like carbon dioxide, are small molecules held by weak forces, so they melt easily. Macromolecular solids, like diamond or silicon dioxide, are giant covalent networks, so they have very high melting points with strong bonds throughout. Let's look at what ionic compounds are actually like. Their strong lattice attraction gives high melting and boiling points, and many dissolve in water as the ions are pulled apart. As solids, they don't conduct electricity because the ions are locked in place, but once molten or dissolved, they conduct well, since the ions are then free to move. They also tend to be hard but brittle, shattering when struck. Simple molecular substances behave very differently. They have low melting and boiling points, and are often gases or liquids at room temperature, because you only need to overcome weak intermolecular forces, not the strong covalent bonds inside the molecules. They don't conduct electricity as there are no free ions or electrons. Non-polar ones dissolve in non-polar solvents. Iodine is a good example, a soft, low-melting solid. Macromolecular structures are the giants. In diamond, each carbon is bonded to 4 others, making it extremely hard with a very high melting point, since those strong bonds must all be broken, and it doesn't conduct because every electron is tied up in a bond. Graphite, by contrast, has layers with 1 delocalized electron per carbon, so it does conduct and feels slippery as the layers slide over one another. Silicon dioxide is another example, a hard, high-melting solid. Metals get their properties from that sea of electrons. Strong metallic bonding gives high melting points, and the delocalized electrons make them good conductors of electricity, carrying charge freely. They're malleable and ductile, because layers of ions can slide past each other without the bonding breaking. Those same mobile electrons make them good conductors of heat, and they have a shiny surface because free electrons reflect light. Let's explain the melting point trend across period 3, from sodium through to argon. Sodium, magnesium, and aluminium are metallic, and the melting point rises across them as each contributes more delocalized electrons and a higher charge, strengthening the bonding. Then silicon, which is macromolecular, has the highest melting point of all because its strong covalent bonds run right through the structure. After that, phosphorus, sulfur, and chlorine are simple molecular with low melting points, though sulfur melts a little higher than phosphorus because its larger molecules have stronger van der Waals forces. Argon, a single atom, is lowest of all. Now, how do we predict a molecule's shape? Electron pair repulsion theory says the electron pairs around a central atom repel one another, and so spread out as far apart as possible. And that's what fixes the shape and the bond angles. You count the bonding pairs and lone pairs on the central atom, treating a double bond as a single region of electron density. And here's the key detail: lone pairs repel more strongly than bonding pairs. Let's run through the common shapes. With no lone pairs, two pairs give a linear molecule at 180 degrees, like carbon dioxide. Four pairs give a tetrahedral shape at 109.5 degrees, like methane. And six pairs give an octahedral shape at 90 degrees, like sulfur hexafluoride. Add lone pairs and the angles get squeezed. Ammonia, with 3 bonds and 1 lone pair, is pyramidal at 107 degrees, and water, with 2 bonds and 2 lone pairs, is bent at 104.5 degrees. Roughly speaking, each lone pair pushes the bonds about 2.5 degrees closer together. Let's predict the shape of water using that theory. Oxygen has 6 outer electrons. 2 of them go into bonds with the hydrogens, leaving 4 as 2 lone pairs. So there are 4 regions of electron density in total, 2 bonding pairs and 2 lone pairs, which arranges them into a basic tetrahedral shape. But the 2 lone pairs repel more strongly, squeezing the hydrogen-oxygen-hydrogen angle down from 109.5 degrees to about 104.5. So water comes out bent, or V-shaped, with a bond angle of roughly 104.5 degrees. Electronegativity is a measure of how strongly an atom pulls on a shared pair of electrons. It increases across a period and up a group. When 2 bonded atoms have different electronegativities, they share the electrons unevenly, creating a polar bond with a slightly positive end and a slightly negative end, the delta plus and delta minus. In hydrogen chloride, for instance, chlorine is delta minus and hydrogen delta plus. But a symmetrical molecule like carbon dioxide is non-polar overall because the polar bonds cancel out. Let's look at the forces between molecules. Van der Waals forces, also called London forces, act between all molecules, and they get stronger as the number of electrons rises, pushing up the boiling point. Permanent dipole-dipole forces act between polar molecules, and strongest of all is hydrogen bonding, which needs a hydrogen atom bonded to nitrogen, oxygen or fluorine, together with a lone pair to bond to. The stronger these intermolecular forces, the higher the boiling point. Let's use that to explain why water boils at 100 degrees, far higher than you'd expect for such a small molecule. Water is small, light and polar. Oxygen is highly electronegative, so the oxygen-hydrogen bonds are very polar, giving each molecule a delta minus oxygen, delta plus hydrogens, and lone pairs to spare. That lets strong hydrogen bonds form between the molecules, and breaking those hydrogen bonds takes a lot of extra energy. So the boiling point is far higher than for similar-sized molecules, and the same hydrogen bonding is why ice is less dense than water. Let's check your understanding. First, draw a dot and cross diagram for magnesium chloride and give the ion charges. Second, why does an ionic compound conduct when molten but not when solid? Third, explain why graphite conducts electricity but diamond does not. And fourth, predict the shape and bond angle of ammonia, explaining your reasoning. A few more to test yourself. First, explain the melting point trend from sodium to silicon across period 3. Second, What 3 conditions are needed for hydrogen bonding? Third, why is carbon dioxide non-polar, even though each carbon-oxygen bond is polar? And fourth, describe how a dative covalent bond differs from a normal covalent bond. Work through those before you move on.